Okay, so in this week's lab, it involved the synthesis of isoamyl acetate, also known as banana oil. And the experiment involves the reaction of concentrated acetic acid with 3-methylbutanol in the presence of phosphoric acid as a catalyst. And the reaction was heated up to form the product isoamyl acetate. And then we use liquid-liquid extraction to separate the product of interest from other compounds within the reaction mixture, and we'll talk about that. But if you take a look at the reaction scheme, and if you're thinking about the mechanism, what might take place, you may consider that, you have the alcohol group, you have a carbonyl oxygen, there's, bond polarity, partial charges. So you might think, the alcohol group will attack the carbon of the carbonyl group. We could draw resonance that pushes the electrons back to the oxygen. Well, keep in mind that what we have in solution is an acidic reaction, and you could think about when, you learned in organic chemistry 1, when you have ring opening of an epoxide, right? When you have ring opening of an epoxide, if that reaction is taking place under acidic conditions, what happens first is that the epoxide is protonated, right? Or the oxygen of the epoxide is protonated, and then that is followed by the nucleophilic attack, right? Well, the same applies in this case, right? Under acidic conditions, the very first thing that will happen is that the acid will protonate that carbonyl oxygen, and then the nucleophile comes in, attacks the carbon of the carbonyl, and those electrons move up to the oxygen. So mechanisms are very simple or very similar in organic chemistry as long as you understand what takes place under specific conditions. Okay, so in this week's lab, we started again with 3-methylbutanol, concentrated acetic acid, and concentrated phosphoric acid. They're all liquids, and we measured each. It was according to the following reaction scheme, and to favor the formation of the product, what we did was use an excess amount of acetic acid. If you increase the concentration of one of the reactants, remember you're going to push equilibrium towards the forward direction to form the product. And phosphoric acid was used as a catalyst to basically it speeds up the reaction by lowering the energy of activation, but oftentimes the reaction would take place using a different mechanism. But this specific reaction was heated up to form the product. And what we did is we used all, the starting material, we put it in a round bottom flask with a stir bar, and then we heated the reaction mixture under reflux. So that was the first time we encountered refluxing a reaction mixture. And the idea is that we'll end up raising the jack so that the heating mantle is really surrounding that round bottom flask. The reaction is being heated up, and what will happen is that it will start condensing right within the round bottom flask. So the idea really of reflux is that you can heat the reaction mixture without evaporating any of the solvent or any of the molecules that are volatile, right? So they'll condense right within the round bottom flask, and then you'll notice that they'll start condensing within the neck, and then they'll go right within the water condenser, and somewhere within the water condenser, however high up those vapor reach, they'll eventually form what we call a reflux ring or a condensation ring. Once you see that, then you start the time of reflux, and that's when we started heating up the reaction for 25 minutes. So it could take 10-15 minutes until you see that condensation ring, and then you start heating up the reaction. Now, the time it takes to reflux a reaction mixture really depends on what we are starting off with, right? And how far that condensation ring reaches also depends on the reaction. But for our purpose, that's where it was. And then we have water running through the condenser. And the idea is that water will basically water is entering from the bottom. So the cool water is basically right where the vapors are. So that will allow the vapors to condense back into a liquid and fall right back into the round bottom flask. And then water goes out from the top and it's falling really right into the drain. And then once the reaction is done, we allow it to cool. What we do is we take that reaction mixture and we add it into a separatory funnel. And what we're trying to do at that point in time is separate what's in solution so that we can extract the product of interest only, right? We'll talk about it in a minute. What is present in the round bottom flask at the end of reflux? So think about it. If that's what we start off with, we're heating up the reaction to form the product, and then we're placing it in a separatory funnel to extract or to separate the products of interest from other molecules. What exactly is present in solution, and what would we add to separate the product of interest? Okay, any questions about this before I move on?
I think you might have people in the waiting room.
Yeah, I have one. Okay, any questions so far? Okay, well, let's take a look at the reaction mixture. What's forming is an ester, but it's a specific type of mechanism known as Fischer esterification. And Emil Fischer and author Speer were the very first two scientists to introduce the reaction where a carboxylic acid group and an alcohol group are heated up under reflux in the presence of a concentrated acid or in the presence of an acid catalyst to form an ester. And it's known as Fischer esterification. And if you recall from last lab, the mechanism involved nucleophilic acyl substitution reaction. You might notice that the mechanism is somewhat similar, where we have a nucleophile attacking a carbonyl group, and then we have one of, a leaving group. The only something to keep in mind is that we're starting with an acid in this case, so we protonate first, and then we do have a leaving group, right? Water will be one of our leaving groups in this case. Okay, so somewhat similar, but doesn't necessarily follow the same exact mechanism. So we'll take a look at the actual mechanism, but we'll take a look at it one step at a time. So the very first step really involves, in the presence of concentrated acid, that carbonyl oxygen will end up being protonated, right? Then you have this protonated oxygen, and we know, I'm not showing you resonance here, but you know that you could draw a resonance, right? That carbonyl oxygen, those two electrons right here, could go up creating a carbocation. So then we have our alcohol group, right? Oopsie, I have an extra. I drew an extra carbon. Okay, we have the oxygen, we have the hydrogen, and we just moved the electrons up to the oxygen, so that creates a carbocation, right? So that molecule is undergoing resonance, is a resonance structure between those two. So the alcohol group then attacks really the carbon of the carbonyl oxygen, which would be a carbocation. Okay, and now it is protonated, and then we'll have the conjugate base of the acid, and that conjugate base will deprotonate the oxygen, and then we end up getting the molecule with two alcohols, but then we have acid in solution. So what will end up happening is that phosphoric acid, or one of the alcohols, will deprotonate phosphoric acid. Okay, now I need to move these so I can actually see. Oops. Okay, and then we have water. We know water is an excellent leaving group, but instead of having carbocation, what will happen is that the oxygen from the alcohol group will go in to form a pi bond. We have water as a leaving group, and then again, the conjugate base of phosphoric acid will deprotonate that proton off of the oxygen, and we end up forming the ester. Notice how phosphoric acid acts as an acid and then as a conjugate base, acts as an acid once again, and then as a conjugate base. Okay, any questions about the mechanism itself? If you can think about what's happening, and why in the order of steps, reaction mechanisms um, really aren't that difficult, right? If you understand how it works, then it doesn't matter what type of reaction you're looking at, you should be able to predict a reaction mechanism based on what you know. Okay, so once we reflux the reaction mixture for 25 minutes, next what we did was liquid-liquid extraction. And what we really wanted to do in that step is isolate the product of interest, right? And we wanted to extract other molecules that are present in solution into a different um, layer, which is basically an aqueous layer in this case. If you take a look at the structure of the starting material, our catalyst and our product, what would be more soluble in the aqueous layer? It would be the acid, right? You have a carboxylic acid group. If you have any alcohol left, like an hydrogen bond, it might be soluble more in the aqueous layer, and then a phosphoric acid would be more soluble in the aqueous layer as well. So the whole idea is that we would like to extract, separate the products between the aqueous and organic layer. I have to move the chat. Okay, so we start by extracting it with water. So what will happen? First of all, if you think about it, what is present in solution? We said that we have an excess amount of acetic acid present in solution, meaning that that will drive equilibrium towards the forward direction, forming more of the product. So if our limiting reactant was used up in the reaction, after reflux, we no longer have any of the 3-methyl butanol in solution. All we have left is our catalyst, phosphoric acid. We have water, because water, it's in water. Water is going to be one of our products in solution. We have acetic acid, and we have our product of interest. So if we go in and that's what we have in solution, and we add water, what will water react with? What will end up being more soluble in the aqueous layer? We added 25 milliliters of water. What's going to end up being more soluble in the aqueous layer? Well, we know that water is an amphoteric molecule. It can act as an acid or a base, right? And, how would you go about thinking about it? What would you think about to decide what might end up being more soluble in water? You could think about acid-base reaction, right? Phosphoric acid is a strong acid. It has a pKa of about 2.1 or I think about 2.1. And then we have acetic acid, which is a strong acid as well. It has a pKa of about 4.8, right? If you take a look at the product, do we have any acidic protons in this case? All we have is the carbon-hydrogen bonds, right? Which are typically have a pKa value of about 50, right? So they're not very acidic. If you think about the pKa of water, it's about 14. So then in this case, water would act as a base, and it would deprotonate the carboxylic acid group and phosphoric acid, making them more soluble in the aqueous solution. Okay, and then we go once again and we separate the aqueous layer from the organic layer, and then we go in and we add 10% sodium carbonate. Now, what is sodium carbonate really doing in solution? If you take a look at sodium carbonate, what might be the role of sodium carbonate? Would it act as an acid? Would it act as a base? It would act as a base. You have the two alkoxide ions, it's resonance stabilized, right? So what it will do, it would actually deprotonate any remaining acid present in solution. So it will deprotonate acetic acid. We have acetate. Phosphoric acid would deprotonate even just from water in solution, but I'm just showing you the effect of sodium carbonate. And you have this oxygen molecule that will end up being protonated from the acid in solution. It would protonate again from the protons in solution. It would end up having a positive charge. What would happen then? That it could be an excellent leaving group, right? And then this oxygen would go in and form a double bond, and that's how carbon dioxide is generated in the solution. And if you watch the video, you could clearly see carbon dioxide gas evolving, and that's just because of the reaction of sodium carbonate. And when I actually ran the experiment, which you won't see on the video that's posted on YouTube, but I'll show it to you right here. Let me just erase all those protons. So you'll notice that the carbon, oh, there it was. Okay, so the pressure buildup, and because of the way I was holding it and not venting it very quickly, some of what's in solution actually spilled off, and that's why the percent yield wasn't as close as it should have been. So it spilled off just because of the amount of carbon dioxide that was being evolved. So venting it very often is very crucial in this case. Okay, could we use any other base, or should we always use sodium carbonate? Sometimes we use sodium bicarbonate, right? Could we use something like sodium hydroxide? What would happen if we use something like sodium hydroxide in this case? All right, if you have an idea, type it on the chat. Could we use sodium hydroxide in this particular experiment? I was going to do a poll, but I won't. All right, could you guys type yes or no on the chat? Could we use sodium hydroxide instead of sodium carbonate so basically water in the presence of some base, sodium hydroxide? Anyone? Okay, well, typically we could use sodium hydroxide. It's a lot easier to deal with sodium hydroxide than deal with sodium carbonate, mainly because in the presence of sodium hydroxide, we won't have to deal with carbon dioxide gas being evolving. But what we have right here is a very strong nucleophiles. And anytime you're dealing with aldehydes, ketones, or esters, those are susceptible to nucleophilic attack. So if we end up using sodium hydroxide instead of sodium carbonate, what might happen is that that alcohol group might attack the carbonyl oxygen of the product of interest, right? So anytime we have aldehydes, ketones, ester, something that could be susceptible to nucleophilic attack, because we know hydroxides is a strong nucleophile and a strong base, then we would use sodium carbonate instead. Notice those oxygens, within sodium carbonate are resonance stabilized. So it's this weaker nucleophile as compared to the hydroxide. Once we have electrons delocalized and one where the electrons are localized right on the oxygen atom. Okay, any questions on the liquid-liquid extraction? Okay, so next we have to calculate really percent yield. We based it based on the volume after we extracted it once again with the with water, and then we poured off the organic layer from the tip of the separatory funnel, and then whatever volume we have, we could use that to calculate percent yield. And we had seen in detail on the synthesis of acetaminophen on how to calculate percent yield, so you can always refer to that if need be. But we're basing it based on the volume of reactant, the limiting reactant that we start off with and how much product it would form. And then we use, you know, the amount that we actually have over the theoretical yield. Okay, and we can calculate percent yield that way. Okay, any questions on percent yield? Should be straightforward. Okay, and then we have to characterize, is the product that we obtained the actual product? Do we have any impurities present? Do we have any of the starting material left in it, or was all of the starting material converted into product? So we could do so by really comparing the IR spectra of the starting material with the IR spectra of the product. And this was the IR spectra of 3-methyl-butanol. And typically what we want to do is tabulate IR data. So in this case, we have a group, we have the alcohol stretch that we can identify at right around, 3,300. And then we have the sp3 carbon hydrogen, and that is right within the range. And then we could also take a look at our product based on the structure of it. We should expect a sp3 carbon hydrogen, or a stretching of the sp3 carbon hydrogen bonds. All we have in this case is sp3 hydrogen carbon hydrogen bonds. And then if we also take a look at the product, you might consider the fact that now instead of the alcohol group, what you have is a carbonyl oxygen, right? So you'll notice the disappearance of the carbonyl oxygen, the disappearance of the alcohol group and the appearance of that carbonyl oxygen within the product. In fact, if we take a look at its IR spectrum, you could see what we get. All right. Is there any other characteristic peaks that we might be able to identify within the IR spectrum? If you take a look at the functional group regions, there isn't really any other peaks to look at, right? That's all, those are the only two functional groups that you have that show any type of absorptions within the functional group region. But if you take a look within the fingerprint region, which we really don't talk about in lecture, but we do kind of point some of them out in the lab, you'll notice this strong, sharp peak at right around 1200 within the product. And then you'll notice also a sharp, strong peak right around 1000 per centimeter within the reactant. What might those absorptions correspond to? If you take a look at the structure of the molecule, what might those absorptions correspond to? See? All right. Well, in the product, we have this carbon-oxygen stretch specific to an ester that shows right around 1180 to 1210. And then anytime we have a primary alcohol, that carbon-oxygen, or the stretching of that carbon-oxygen bond, specifically for a primary alcohol, shows up right around 1000 per centimeter, right? So there are other characteristic absorptions that we could tell within the fingerprint region, especially when they're strong and sharp as such. right? So not only could we tell that we have an alcohol group, right? This alcohol group, based on its absorption, is actually involved in hydrogen bonding. Alcohol groups that are not involved in hydrogen bonding typically will have a slightly higher wave number. It could be anywhere between 37 and 3,500, whereas if the alcohol group is involved in hydrogen bonding in solution, it's typically less. So not only is this an alcohol group, but we could tell that's also involved in hydrogen bonding. Okay, and then we have the carbonyl group within the product, right around 1735, and anywhere between, I believe 1735 and 1750 is a carbon-oxygen stretch specifically for an ester group. So not only do we know that we have a carbon-oxygen stretch, we can also specifically be able to identify that it's a carbon-oxygen stretch or a carbonyl oxygen stretch associated with the presence of an ester, and we can further confirm that by finding that carbon oxygen stretch within the fingerprint region, right? That oxygen carbon stretch shows a clear, strong peak right around 1200. And in the case of a primary alcohol, its stretch is really right around 1,000 per centimeter, right? If you take a look at an IR spectra closely, you could definitely identify that the product has been converted, that the reactant has been converted into product, and that we don't have any of the reactant left in solution, right? Notice, you don't really have this alcohol peak in the product. So all of the reactant has been converted into product. Okay, any questions on IR? Okay, so another way we could characterize the product is really by means of NMR spectroscopy, or proton NMR in this case. 1D proton NMR. Okay, so, you look at an NMR spectrum, or you're given a molecule and you're kind of trying to decide, where do you start? You could start by taking a look at a peaks that are shifted more downfield or higher parts per million, right? Those could be peaks that are associated with protons that are next to the atoms that have high electron densities. So you have this oxygen atom, okay? Nearby, you have those two hydrogens right here. Well, nearby, that ester group is also a carbon right here that's attached to 3 hydrogens, okay? But those 3 hydrogens are directly attached to a carbon, whereas those 2 hydrogens that are attached to this carbon are directly attached to the oxygen. So I would expect that those protons would be the ones that are shifted the most downfield, right? Closest to that electronegative atom. Well, we could also identify it based on splitting pattern. So the peak is split based on nearby protons. So if we take a look at those 2 protons on this carbon, those 2 protons will show a single peak. But that single peak will end up being split based on what's nearby. And that's when we use the n+1 rule, right? Where n is referring to neighboring protons. Well, one bond away to the left, it's simply attached to an oxygen, whereas one bond to the right, there is a carbon, and this carbon is attached to a hydrogen. Okay, so then n is the neighboring proton. So n in this case is 1. So we say 1 + 1, which is 2, meaning that that peak should be a doublet, right? So that's one way to confirm as well that it's a doublet. Okay. And then you would do the same for everything else. So we're going to just take a look at that. Those 3 hydrogens on the same carbon have the same exact environment. One could hydrogens on the same atom have different environments. When you have something like an alkene and you have protons across an alkene, you can't rotate around a carbon-carbon double bond. So the protons across an alkene, this hydrogen and this hydrogen do see slightly different environment, right? Think about it that you can't really rotate around that carbon-carbon bond, so those two hydrogens could see different environments. But in the case of a carbon-carbon single bond, they're exactly the same, right? So those three hydrogens would correspond to one peak, and that one peak will end up being split by nearby protons. So that again would be n+1. And if you take a look one bond away, this is a carbon that's not attached to any hydrogens. So n in this case would be 0. So 0 plus 1 is 1. So that would end up being a singlet. Well, that singlet is closest to the ester, so it should be also closest downfield to that doublet. And indeed, this is the only singlet in this case. So that would correspond to this proton. Okay, well, now let's take a look at this proton right here. Well, on this carbon, there's one proton, okay? So that's 1, but what we have to do is take into account n+1. Okay, so we have to take into account the n+1 to indicate how it's being split. Well, this carbon that's attached to a hydrogen is directly attached to this carbon, and this carbon is attached to 3 hydrogens. Okay, well, one bond away is another methyl. Those two methyls have the same exact environment, so they count as, the same thing, right? They have the same exact environment. So this hydrogen, how many nearby protons does it see? 6 nearby protons. So this N is really 6, all right? 6 plus 1 is 7. But what you learned in Organic Chemistry 1 is that if you have a hydrogen or a proton that's attached to protons on either end that experience different environments, what you end up having to do is the n+1 rule twice, right? So we have to do the n+1 rule again. We already have those 7 peaks, but now those 7 peaks are going to be split. Those 7 peaks really now correspond to this 1, right? They're going to be split by neighboring protons. And one bond away, we do have 2 hydrogens, so that's 2 plus 1, or 3. So what you end up getting is 7 peaks, and each of those 7 peaks are split into 3 more peaks each. Or 3 peaks, and each of the 3 peaks is split into 7 peaks each. So what you end up getting is a triplet of a septet, right? And I'll show you on the next slide. I'll zoom into it, all right? Some of those peaks might overlap, so you might not necessarily see that many peaks, but it's a triplet of a septet based on using the n+1 rule twice. Sometimes you'll just simply see it being written as a multiplet, all right? And now the only thing that is left is those 2 methyls. Those, this methyl and this methyl have the same exact environment. They'll count as 1. And then again, we do the n+1 rule. One bond away, we only have a single hydrogen, so that's 1 plus 1. So that's 2, so that's a doublet, and we have a doublet right here. So you have 2 doublets, right? Based on the intensity of the peak, the area under this peak has more hydrogen, so it would correspond to those protons, right? As opposed to those protons. And those protons are more downfield. So that's how you would assign that this is the doublet that would correspond to those protons, right? What we typically do on a software when we're analyzing the data is that we'll integrate the area under each peak. And if we have a reference like CMS at 0 parts per million, we can assign, after we integrate, we know the number of protons, we can assign that to it. But integrating it and then setting it up based on a reference, the area under that peak will tell us the number of protons that each peak corresponds to, right? It's not necessarily the height, it's the area under the peaks, and you consider all the peaks. Okay, so and then that's how, that's what we would end up getting. Any questions on proton NMR? I know that's mostly from lecture, mostly from organic 1, but you do talk about it quite a bit in organic 2 as well. It's a lot simpler than you might think, as long as you know how to tackle a proton NMR spectrum. Okay, any questions about that? Yeah. Any questions about this lab? Jasmine, was acetic acid extracted with 10% sodium carbonate? Also, what was extracted with the last addition of GI water? Perfect. Let's go back. Okay, so remember, all you have in solution are those molecules, and then plus water. And then we extract water so that we can extract phosphoric acid and acetic acid into the aqueous solution. And then we keep the organic layer. Now the organic layer still has some acetic acid and some phosphoric acid. So we go in further and we extract it with sodium carbonate. And then we dispense the aqueous layer and we save that just in case. And we save the organic layer. The organic layer in this case might still have some phosphoric acid and some acetic acid. So we extract it, yes, yet once again with DI water. So what we're doing is multiple extractions to ensure that we don't have any remaining, molecules in solution aside from the product of interest. So both water and sodium carbonate are extracting acetic acid and phosphoric acid into the aqueous solution. Does that help? Perfect. Any other questions? Okay, if we don't have any questions about this experiment, I will, stop the recording and then take in questions you may have about the poster. So any questions about this experiment itself? What was the mass? So we didn't weigh the mass, it's the volume, right? And if you know the volume, isoamyl acetate at the end of the experiment, and we know the density of it, we can calculate its mass, right? Volume in milliliters times density in grams per milliliter, right? Volume times density will give us the mass.